Alright, yo, this video I have something pretty juicy, if I were to be completely honest with you. We're going to be talking about the PN Junction, probably one of the most important inventions in all of human history, because we'd still be living in the farmlands without computers and other cool stuff. But before we start, this video is sponsored by GLC PCB. So, yeah, what are you doing? Create some PCBs with GLC PCB. Anyways, let us begin. Okay, so let us begin. So the first thing we need is some sort of semiconductor material. Usually it's silicon or germanium. And the reason why they use these is because if you look at the periodic table where carbon is, carbon has 4 valence electrons. And this is something special about carbon, like that symmetry allows it to connect to lots of things and create extremely complicated geometries. And that's how life and humans and biology is created. But if we go under, we see silicon and germanium, and that's where robots and artificial intelligence is truly made out of. But there's something called a p-type and there's something called an n-type. So you dope the silicon or germanium with, you dope it with holes. Let's just call them holes where electrons should be. And the n-type would have an excess of electrons. Okay? And right now the p and n-type are not touching, but when we do connect them together, you get a PN junction. Right? And what would happen is, okay, let's just say this was our P region, this is our N region. We're going to get some width, the depletion width. And we're going to have negative charges build up over here, and positive charges build up over here. And there's going to be an electric field going across called the built-in voltage. We're going to get a built-in voltage right in the middle of our PN junction. And we're going to calculate this width. And something really juicy is that this is kind of like a capacitor. Right? We have 2 plates of negative and positive charges. So really, we can create capacitors out of diodes, and there's a thing called varactor diodes, and they're used a lot in RF and radio electronics. Well, RF and microwave electronics, but that's another story. Let's try to calculate our depletion width. So if you take a look here, we have a plot, and on the y-axis we have charge, and on the x-axis we have our distance. And I'm aligning this up with our depletion region, so you can see we have a negative and a positive region. And well, we really want to get our voltages. And to get our voltages, we need some sort of charge density. But what we have here is just charge. To get our charge density, well, let's do our negative region first. So we want to find our charge density. Then we can integrate that and get some voltage. Okay, but maybe I'm jumping too ahead. Let's first find our charge density in our negative region. Right? So what's it going to be? It's going to be some negative Q, some negative electric charge, times, well, I forgot to mention, Na and Nd. These are concentrations of our acceptor and donors. Right? So we're going to multiply by our acceptor concentration, but we need the Q. Well, all we have is negative Q times Na, that's that, but we have to find the density. So we just multiply it by this length, and we should just define our length as xp for our P region, and we should call this one xn for our N region. So now we just need to multiply this by xp. Okay, so that's for our negative charge density. Now to get the positive region, all we're going to do is we're going to have a positive Q now. So we have positive Q times our donors times xn. Right, so this is our charge density. Now we can do some integration, get the voltage, find the built-in voltage from the electric fields that are within this PN junction, and then we could find our xn and xp by solving a system of equations. Now, before we find our built-in voltage, I think it's important to say this PN junction is right now net neutral. The net neutrality of this entire block is neutral. So what we could really say is 0 is equal to our P of our negative charge density plus our positive charge density, right? So what we're going to end up with is, we're going to just end up with Q Na xp is equal to Q N dxn. Q's cancel out, and wait, we could solve for, let's just do xp. Xp is equal to our concentration of donors times our negative region depletion with length divided by Na. And this is actually going to be pretty useful, so I thought it was pretty important to just get this out of the way before we find our built-in voltage. Okay, so what we're going to do is we're going to find our electric field, and from our electric field we could find our voltage, right? And then we can do that for both the N and P type regions, sum up that voltage together, we get the built-in voltage, and we do some algebra using this guy to finally find our depletion widths. So, and we really want to find the absolute value of our electric field. We don't care about the sign because we need to find the voltage drop. So sometimes there would be negative, sometimes there would be positive. It doesn't really matter. We're going to take the integral from 0 to x, let's just do xp, okay? And what are we doing? We're going from some charge to, and for our p, it's going to be Na on epsilon dx, right? So this is an expression for our electric field. Now, there's no dependence on there's no x's inside of our integral, so we're really going to end up with q Na over epsilon, and we just evaluate this integral from 0 to xp, and this will just end up being q Na xp on epsilon. Right, so that's our electric field for our P region. Now we could go through the same thing, but it's pretty trivial. We could just flip the symbols around. So now we have our donors, we have our xn region on epsilon. So now we have electric field for our N region and our P region. So now let's find our voltages associated. Okay, so I just left the negative electric field here because we just need to find one of them, and then the other one is pretty trivial to find. So our voltage, we don't care about any signs here, is going to be the integral from 0 to xn, and we're going to plug this in there. So qn dxn on epsilon with respect to xn. And since we have a linear guy inside of this integral, we're just going to end up with a half quadratic boy. So we could write our voltage now as qnd on epsilon, and we're going to evaluate that from xn on 2 squared from 0 to xn. And all we're going to end up with here is we're going to get qnd on epsilon times xn squared, and we have a factor of 1/2 right there. So wait, let me just, where did I put that? So we could trivially find our voltage in the positive region. So this is our negative region. So Vp would just simply be, we're just going to switch that to a acceptor concentration. So Q, N, A, and then our positive width on 2 epsilon. So now what we're really going to do is to get our voltage built in, we're going to sum together our Vp and Vn. So let's just do that quickly. Alright, so now we have our an expression for our built-in voltage. It's just our negative region voltage plus our positive region voltage. And we have an expression or an equation for our depletion width in the positive region. So we could take that and substitute it in right there and then solve for Xn. And we'll get it in terms of VBI, concentrations, and XPs. So let's go do that right now. So first thing we could do is we could factor out the Q over 2 epsilon. And what would happen is we'd get 2 epsilon times our VBI on Q. And then that's going to equal to, well, our donor concentration, Xn squared, plus, well, we have a ND squared over here. We have an Xn squared over here, and we have just a factor of NA left over, because that guy canceled with this guy. So now we could just factor out an Xn, divide by the dude. So what's really going to happen is we're going to have Xn is equal to the square root of 2 epsilon VBI over Q times NA. ND. We're going to factor out an ND. And what we're going to be left with is a 1 plus ND over NA. Is that right? Probably. But yeah, we just got our Xn depletion region. Oh my god. Okay, so we have our expression for our negative depletion region. And to find the positive depletion region is pretty trivial, because all we have to do is switch the concentrations around. So now we have acceptor concentration times 1 plus the acceptor concentration over our donor concentration. And there you have it. The depletion regions of a PN junction diode, boy. Woohoo!